All right, hi everybody. I'm trying a new software here, so please bear with me. I hope this works. And okay, so far so good. Fingers crossed. So, okay, here we go. Um, oh no. All right. So, yeah, I was asked to do this problem here. It says a cyclotron is used to produce a high beam energy deuterions that can then collide with a target to produce radioactive isotopes for medical procedure. Deuterions are nuclei of deuterium, an isotope of hydrogen consisting of one neutron and one proton. So, with a total mass of 3.434 times 10 to the negative 27 kilograms, deuterions exit the cyclotron with a kinetic energy of 5 mega electron volts. So they asked me what's the speed of the deuterions when they exit. All right. So I'm going to use, so this is, problem 30 was asked for me from chapter 24. So I'm going to use the fact that this thing's moving with kinetic energy. Right, they gave me the kinetic energy of 5 mega electron volts that can be just converted into joules with a quick Google search. Then we also got the mass of this thing is 3.34 times 10 to the negative 27 kilograms. So I can use then the equation for kinetic energy to figure out what the speed is because they gave me the mass. So I can multiply both sides by 2 here. I get 2k and then also divide by m and then take the square root of both sides and I get the velocity. So the velocity is going to be the square root of 2 times my kinetic energy in joules divided by 3.34 times 10 to the negative 27 kilograms. So that's negative 27. And there we go. But we got to convert to joules here. So I have this set up here. 1 mega electron volt is 10 to the 6 electron volts. And then 1 electron volt is 1.6 times 10 to the negative 19 joules. Again, that's the amount of energy it takes to move an electron 1 volt. Yeah. All right. So to do this then, you're going to do, let's see, mega electron volts. So it's 1 MeV is 10 to the 6 eV. So my mega electron volts cancel out. And then I get 1 eV is 1.6 times 10 to the negative 19 joules. Again, EVs cancel out. So I can calculate this all out. And I get 5 times 10 to the 6 times 1.6 times 10 to the negative 19. And I get 8 times 10 to the negative 13. Whoa. So there we go. And I'm going to plug all that in there. So this becomes 8 times 10 to the negative 13. And then I will calculate all that out. So times 2 divided by 3.34 times 10 to the negative 27. And I take the square root of all that. And I'm getting 2.19 times 10 to the 1, 2, 3, 4, 5, 6, 7. So I'm getting as an answer 2.19 times 10 to the 7 meters per second. This is fine. It's under, so again, the speed of light is 3 times 10 to the 8 meters per second. And as long as it's under that, that's good. So this is definitely less than that. So there we go. And there's my answer. Looking good. All right. And yeah, we got a, a particle moving at a high velocity. That makes sense. Then next up, they say what's the magnetic field inside the cyclotron? If the magnetic field inside the cyclotron is 1.25 Tesla, what is the diameter of the deuterion's largest orbit just before they exit? So we got something that's orbiting like this. So I gave it a radius r, and then if it's moving in a circle, so it would have a tangential velocity like this, which is going to be our speed up here. And then here's the magnetic field. The magnetic field could be pointing wherever. I'm not going to worry about that right now because I just want a calculation. No need for right-hand rule or anything like that. Because it's one positive charge and one neutron, it's just going to have the charge of one positive charge, which is 1.6 times 10 to the negative 19 coulombs. And so, yes, and then the reason that it moves in a circle is because of the magnetic force causing it to move in a circle. So I'm going to use an oldie but goodie. That's Newton's second law, that the net force is equal to the mass times the acceleration. In fact, we did this when we dealt with the mass spectrometer. This is just a different machine doing a similar thing. We saw it also with the oscilloscope. Okay, so the net force here is the magnetic force, and that's going to equal mv squared over r. Let's see. So then next up, and by the way, my goal here, they're asking me for the radius, right? Well, the diameter. So I'm going to find the radius, hopefully, and then from that, I will find the diameter. All right, here we go. So magnetic force for a charge, that's going to be QVB sine of theta. But my magnetic field would be pointing either into the page or out of the page. In fact, I can figure this out really quickly here. So my velocity goes to the right, and my magnetic force points down. That means then the magnetic field must be pointing out of the page. So my magnetic field is doing this, and that's from an external magnetic field. So yeah, and that's going to be this external magnetic field. So it's going to be EXT. And so the angle at any moment, you know, as the velocity changes, let's say the velocity is here now, right? Well, the velocity is pointing down. The magnetic field, the external magnetic field would still point out of the page because that's coming from an external source. So it's going to be constant, and there's still 90 degrees. So the velocity is always 90, and sine of 90 is just 1. So then this becomes equals mv squared over r, and I can see also this velocity is going to cancel with that velocity. I can multiply both sides by r. That's going to give me q times the external magnetic field times r equals mv. I can then divide both sides by qb external. And I get, so let's move this down a little bit here. There we go. I get this cancels, and then I get finally that the radius, right, is going to be mv over qb external. And so if I plug in then my values, again, the mass was 3.34 times 10 to the negative 27. The speed that I calculated before, 2.19 times 10 to the 7. Charge, again, it's just going to be the elementary charge because it's 1 proton, 1 neutron. So 1.6 times 10 to the negative 19 coulombs. And then multiply by that external magnetic field, which was 1.25 Tesla. So if I plug all this in, give me a second, it's going to take a little bit. I got 3.34 times 10 to the negative 27 multiplied by 2.19 times 10 to the 7. All of that divided by 1.6 times 10 to the negative 19 coulombs. It's the elementary charge. And then multiply that by 1.25. And I get 0.366. So my radius is 0.366 meters, but they want the diameter, and the diameter is always twice the radius. So that's going to be 2 times that size, so 0.731. And there we go. There's my diameter. All right, moving right along. So lastly, then they ask me if the beam of current is this much microamps, I'll give the conversion of micro in just a bit. How many deuterions strike the target for each second? So this, I think I'm going to use then the definition of current. It's the amount of charge divided by the change in time. So it's how quickly charge moves with time. Okay. And then they gave me a current of 400 microamps. So microamps is times 10 to the negative 6. And then I can figure out how much charge that is, and that much charge should, well, anyway. So here we go. I can multiply both sides by delta T. I'll get I times delta T is equal to the charge. So again, my current is 400 times 10 to the negative 6. And then the each second. So they told me each second. So okay, so that'd be 1 second then. Sorry. Pausing there, I was like, wait a minute, I don't got a time. So it's just going to be 400 times 10 to the negative 6. But that's coulombs of charge, right? That's coulombs of charge. And so, again, my what do they call it? A deuterion is just one proton's worth of charge, because one proton, one neutron, so it's just the proton that's going to matter. So if I have that many coulombs and one proton, well, one proton is 1e, and that's one elementary charge, and one elementary charge is just 1.6 times 10 to the negative 19 coulombs. Again, we could look that up, but if I use this, so I'll just copy this right here, and I'll paste it down here. So using that, that's just a direct conversion factor like you used to do in chemistry. So I'm going to have 400 times 10 to the negative 6 coulombs. And at the bottom here, I'll have 1.6 times 10 to the negative 19 coulombs. And that's equal to 1 elementary charge. So the coulombs cancel out. And if I do this calculation, I get 400 times 10 to the negative 6 divided by my elementary charge, which is 1.6 times 10 to the negative 19. And I get 2.5 times 10 to the 15. So 2.5 times 10 to the 15. And that's elementary charges, but that's also equivalent to my deuteriums, because one elementary charge is the same as one deuterium molecule. So I could say, or they didn't call it deuterium, they called it deuterions. So there we go, I hope I spelled that right, because I just lost it. Anyway, I'll just scribble it. There you go. You can't tell anyway. So yeah, there you go. And there's that. So there's that for part B. And yeah, okay. Hope that helped. Bye.